So this part from section from chapter 5 is inserted here because it's now become relevant, where we need to be able to determine the mass of molecules and other compounds. So this is not surprising whatsoever. We already talked about the mass of an individual atom. Right, so if I have a mass of hydrogen, I get that from the periodic table. The mass on the periodic table represents what? The average mass of the naturally abundant isotopes depending on their ratios of natural abundance. Right, so when I'm dealing with an individual atom of hydrogen and I want to know its mass, I have to know which isotope I'm dealing with. Is it a hydrogen, or is it deuterium, or is it a tritium? Because hydrogen, deuterium, and tritium have different numbers of neutrons and they have different masses. And if I only have one atom, I need to know how many neutrons are in that atom if I want to know what its mass is. If I have a sample of hydrogen that's a natural sample of hydrogen and it's not isotopically enriched in any way, then I use the mass on the periodic table. Because the mass on the periodic table tells me if I've got a naturally occurring sample of hydrogen, there are a variety of isotopes in there, but on average, the mass of an atom will be equal to whatever the mass is on the periodic table. Normally, that's what we're dealing with in the lab. We're not just dealing with one or two atoms with specific isotopes, right? Or some isotopically enriched uranium or something, unless we work in a nuclear power plant. But if I've got a naturally occurring sample, I just add the masses of the periodic table, right? So for water, it's got 2 hydrogens, 2 oxygens. Take the mass of hydrogen, multiply it by 2, since there are 2 of those in the formula. Take 1 oxygen, add it together. That gives me the average mass of a water molecule. There's such a thing as heavy water. Heavy water is water that has deuterium instead of hydrogen. So if you happen to buy that, you can buy water where all the oxygens have deuterium instead of hydrogen. Meaning all the oxygens have a hydrogen with an extra neutron. That water molecule has a heavier mass because in that case each hydrogen has a mass of 2. Added to the oxygen's 16, that gives you a mass of 20. That individual molecule is heavier. But that's not natural, that's not the way water naturally exists on Earth. Water exists as a mixture of isotopes with an average mass of 18.02. So we can call that the molecular mass. That's probably the best term for it because it's the most descriptive. It's the mass of one molecule on average. So if I have one molecule on average, that molecule's mass or its molecular mass will be 18.02 AMU, right? Because an AMU is about as heavy as a proton or a neutron is. So we're adding up on average how many protons and neutrons there are in that molecule. Another term for that is called molecular weight. Not quite as good of a term because we're not really looking at the weight, we're really looking at the mass. But those two are still often used interchangeably. We can use the term molecular here because our water is a molecule that has atoms sharing electrons. If the atoms weren't sharing electrons, it wouldn't be a molecule. And we wouldn't use the term molecular mass, because the molecular refers to a molecule. So what would we use? We would use a more general term called formula mass. So formula mass includes molecular mass. So formula mass is the mass of a compound that includes molecules and it includes other compounds like ionic compounds that are not molecules. So for water, it's also its molecular mass. We found out that was 18.02 AMU. For sodium chloride, that's not a molecule because the sodium and the chlorine are not sharing electrons, right? Between a metal and a non-metal, the sodium needs to lose its electrons to make its noble gas configuration. It needs to take on a positive and not share, because if it shared, it wouldn't have the same number of electrons as a noble gas anymore. So that isn't really a molecular mass, it's just a formula mass, but we could still calculate it. So we look on the periodic table. On average, the mass of chlorine, 35.45 AMU. On average, the mass of sodium, 23.00, I think. No, 22.99 AMU. So we just add those together. That would give us the formula mass. So the formula mass is the average mass of one of the repeating units that that compound is made up of. Could be a molecule, might not be. So make sure you understand the difference between those terms. And then, this is really easy. Students usually don't have a problem with this. You just have to take the elements, find them on the periodic table, and add their mass together. So let's just do one. Let's just do C3H8. So C3H8 is propane. It has 3 carbons, 8 hydrogens, just the number it needs to complete its noble gas configuration for each carbon and each hydrogen. If I want to know the formula mass, in this case it would also be the molecular mass since it is a molecule. If I want to know the mass of that, I just have to figure out how heavy each carbon and hydrogen is and add them all together. So I've got 3 carbons. Each one, on average, has a mass of 12.011. Right? That's the average mass of a carbon atom. I've got 3 in that molecule. I'm going to add that to that. I've got 8 hydrogens. Each one of those is 1.008 AMUs on average. When you use your periodic table, some periodic tables give more decimal places than others. This one gives a lot. For hydrogen, it says 1.00794. I round that up to 1.008. That's fine. Okay. When you use your periodic table, you could use 2 decimal places. If your periodic table gives 3 and you want to use 3, that's fine. I don't really care too much about that. Try to be consistent, though. So use at least 2 decimal places. Don't round up to the whole number or something like that, because that will skew your answers a little bit. So then I just have to plug that into my calculator. Just so easy. I feel like I'm wasting your time doing it. So I'd multiply 3 times 12.011, add that to 8 times 1.008, and I get a mass of 44.10 AMU. Actually, I had 3 decimal places of certainty in each number, so I should be able to go out to 3 decimal places of certainty here. Right? Adding and subtracting, rule for sig figs is we line these numbers up and see which columns we have certainty in. And I have certainty in the tenths place, hundredths, and thousandths place, so I can have certainty in each one of those 3 decimal places in my answer. But again, that's the average mass of a molecule, one molecule of propane, right? That's why we use units AMU, because that's for individual protons and neutrons. So on average, a molecule of propane has about 44 total protons and neutrons. Any questions about that? Okay. You probably just need a little practice with those and you'll be good. If you have any questions about them, please let me know. So then we talked about this last bit already. If we wanted to determine quantitatively how much faster, if they're at the same temperature, they have the same average kinetic energy, which is determined by both the mass and the speed. If they have the same kinetic energy, we know the one with less mass has to have more speed, so when we multiply, we get the same value for kinetic energy we do for the one with more mass. But if we want to know how much, then we can use the formula that we talked about. So this formula is a ratio. It tells me the speed of one substance, depending on its mass, versus the speed of another substance, depending on its mass. And so if I have 2 substances, we've got helium versus carbon dioxide. Now we know for a formula how to figure out that mass. I would add the mass of one carbon and 2 oxygens to get the mass, the average mass of a carbon dioxide molecule. So instead of working with these units, let's just keep working with AMU. So this is the mass of helium. This is the mass of CO2. So then I would plug those in. So we'll keep these units. Plug those into the formula, right? So if the helium is going to be the lighter one, I probably want to make that one on top here. That's going to give me a number that's greater than 1 and more relatable to me. So I take the lighter substance. That means its mass goes on the bottom on the other side. The heavier substance on the bottom on the left, its mass is going to be on the top on the right-hand side. Right, so I'm just plugging into this formula. Put these numbers in my calculator, divide them, take the square root, and I get 3.316. So that means if they're at the same temperature, on average, a helium atom is moving about 3.3 times faster than the average carbon dioxide molecule.